So for tonight's lesson, we'll be looking at some quadratic word problems. These will involve finding the max or min values and finding the roots of the equation. So from last time, we should know how to graph quadratic functions, find the vertex, the intercepts, find the equation from the pattern and from the graph, and change from one form to the next. So there are basically two types of word problems that we'll look at. There are those that ask you to find the vertex, and those that ask you to find the roots. Sometimes they can give you the equation and ask you to do this. Other times they'll give you the information to find the equation. And this finding the equation, much more difficult. So we'll do the vertex questions first, and then we'll look at finding the roots. So if you recall finding the vertex, we can use x equals minus b over 2a, and then plug it in to find the y value of the vertex. So here I'm using function notation for that. This f of minus b over 2a gives us the y value of the vertex. And we know that the y value is either a maximum value or a minimum value. And so if it's a minimum value, that's going to be when a is a is greater than 0, and that's because there's no reflection, and you can see the minimum value here is the y value of the vertex. There's no restrictions on the x values. Remember, the domain is xer. And so there's no maximum or minimum value for the x values. It's always the y value. And so if the a is less than 0, then we know the graph's been reflected, and the y value, again, of the vertex is a maximum. So let's take a look at an example where they will end up giving us the equation right here. So small business profits represented by this function. R is the revenue measured in thousands of dollars, and P is the price of the product measured in dollars. So the first question is what price would maximize the revenue? So I'm looking for price. My answer is going to be P equals something. The word maximize here is going to tell me that I'm looking for the vertex. Okay, and I know how to find the vertex. That's minus b over 2a. Now notice here I didn't say x equals, I said p equals, because that's the variable that's being squared there. So when I plug in my b value of 64 and my a value of negative 0.4, I see here that I get a value of $80. Okay, so the price that would maximize the revenue is $80. Now, of course, the next question is, well, am I going to be able to send my kids to college here? What is this maximum revenue possible? And so we're looking for the y value of the vertex here. So I know the x value. I'm going to plug it in, and I see that I make the revenue here is 160. However, you have to recall that the revenue is measured in thousands of dollars, so this is $160,000. So this is the best price. It's $80. Just very quickly here, it's a sketch. The graph kind of looks something like this, and you can see that if I don't sell it for enough, I'm not making enough on each product, and I'm going to end up owing money. I'm going to lose money. Conversely, I guess if I charge too much, I'm not going to sell enough, and I'll end up losing money as well. And over here, of course, what the values where I'm starting to make some money, and I see that I'll have the best price here. And it will make me, according to the equation that models the data, 160,000. So question B would be how much money would they lose if they gave the product away? So here I'm talking about a price of 0. So wherever I see a P, I'm going to plug in 0, and I would lose $2.4 million, which is probably why if you only have one product in the business, you don't give it away. So that's a pretty straightforward example. I give you the equation, the word maximize or minimize or most or best or worst, or as my kids say, worstest. Those nouns, or I don't know what those are actually, those words tell you to find the vertex. And so you're going to use x equals minus b over 2a. But here's an example where we don't have the equation. So this is a lot tougher. So we have this farmer. He needs to fence off his farm according to these dimensions. We've got this pig pen, we've got this sheep pen, and then he's got this area for his kids. Now, I don't think that's actually for his children, although that would be a good idea to be able to fence in your kids. Anyways, this is probably for the the baby goats and stuff. I think they're called kids. In any case, what we have here is this length is W, and this length is 3 of those, and so is this one. And this length is 2L, and this is 4 of those. So every line on this is a piece of fence. And so the question is, what's the dimensions of the largest area? So what we have here is a question that's we're trying to maximize maximize area, but there's a constraint. And the constraint is that we only have 800 meters of fence. Now, if I just said, what's the largest possible area I can make with these relative dimensions? Well, you can make it infinite because you don't have any restrictions. Well, obviously a farmer would have a restriction on how much fencing he has, so this is going to come into play, and we'll start with that actually. If we take a look and we realize that this 800 meters of fence is every line here, we've got 3W and 3W and 3W and 1W. We've got 8L, 2L, and 8L. So if we add those all up, he has 10W plus 18L equals 800. Okay, so there's our constricting or restricting equation. Okay, but it has 2 unknowns here, and so what we need is the other equation. So if we look at what's being maximized, let's get the area equation. Now I'm trying to maximize all of this, so the area is simply length times width. That was supposed to be a straight line. So what we have here, whoops, I don't know what's happening to my little thing here, sorry about that. So what we have here is the area is going to equal 3W times 8L, which is 24WL. So now I have 2 equations. They both deal with the same variables, and so this is a system of equations. And so what we're going to do is we're going to substitute. We're going to take the restricting equation and solve it for a variable and plug it in here. Notice that I know that I'm heading to the vertex. That's what I need to get. I need x equals minus b over 2a, but I don't have a quadratic yet. So I'm going to take the restricting equation, plug it into the area equation. Goodness me, sorry about that. I messed it up again. In any case, so here's how this looks. I'm going to take the restricting equation, solve it for W in this case. That's not random, by the way, because I looked at this and I said, well, I'll have to divide by 10. And dividing by 10 is very easy, certainly easier than dividing by 18. So you could have solved for L, but I solved for W. I'm now going to substitute this into the area equation. And so now I can take 24L and multiply it by 80, and then by negative 1.8L. And lo and behold, I get a quadratic. Now it's very important you recognize that this 1920 is the B value, because it's in front of the L, not the L squared, even though it's written first. Really, I made up this equation, so it doesn't have to be in any set order. And you'll notice here again that this negative 43.2 is in front of the L squared. It's the L squared coefficient, so that's my A value. So now I'm going to find the maximum area, or the dimensions here. So I'm going to use the vertex equation. L equals minus b over 2a. Plug it in to that. Solve for that. And so this is the best L value. And I need the W value. And the W value is 40. So the dimensions here would be 120 and then whatever 8 times 22.22 is. Okay, that would be the dimensions of the largest area possible. And so if we find the area, I don't think we were asked to here, but if we find the area, we get this value, and that's the biggest it can be. So what we did there was we set up the constraint equation. We had 800 meter fence, so that restricts us. We set up the area equation. It was an area of a rectangle ultimately. And we plug in the restricting equation into the area equation and solve for the vertex. So here's an example here you might want to try. A lifeguard has 75 meters of rope to section off a supervised area of the beach. What is the largest rectangular swimming area possible? So of course, at the beach you don't need that fourth side of the rectangle. All right, you don't have to fence this part off right here. People kind of know where the beach starts, where the water starts. In any case, you might want to pause the video here to try this yourself, but I'll go through it as well. So we have a restricting equation. I'm going to call color here. I'll call this W. That means this is W and this is L. And so these can be anything I want, except this is the equation. 2 W's plus an L has to give me 75. So just for instance, I can make this something like this, where this is 25, this is 25, and this is 25. Well, that means the area is 25 squared, which is 625. Now that's just a guess. I could also say, well, let's make this really long. Let's say that this is only 5 here and 5 here. And that would make this, well, if I've used up 10, that would make this 65. And so when I multiply this to get the area here, I get, what is that, 325. So clearly this is not the best one. 325 is a lot less than 625, so this is my best option so far. But I could try this again. I could try 30 here. And that's 30, that's 60, that's 15 here. And so this would be 450. Oops, that's not good. This is still my best option. Let's continue here with the math to see if this 25 by 25 is the best. See if 625 square meters is how much I can guess here. So the area equation is going to be length times width. I'm going to solve the restricting equation for the variable. One of them, again, L here is a little bit easier to solve for than W. It doesn't really matter which one you choose. I'm going to substitute this into the area equation, and I get a quadratic as I multiply this out. I'm looking for the largest possible rectangular area. That means I'm looking for the vertex. And so I'm going to take this equation, identify the B value, identify the A value, and I'm going to plug and chug. So the best value is not 25 as I guessed earlier, it's 18.75. And so the question asks, what is the largest rectangular possible, or largest possible rectangular swimming area? So I'm going to now find the area here, and I see that it's 703.125 square meters, bigger than the 625 that we had. And I found that by using this W and plugging it in, plugging it in. All right, so now let's take a look at. We'll take a look at some equations that deal with the roots. They're not going to be maximized questions. They're not going to be find the vertex here. These are going to ask us to solve for values. And so we know that we can solve for the roots of a quadratic if we have the function equal to 0, and we can sometimes factor. We can complete the square, or we can use the quadratic root formula. And the quadratic root formula, I think, is the best way because it works every time. It's easy to do. You kind of get into a routine of it. So let's take a look at an example here. A duck dives underwater and its path is described by the quadratic function y equals 2x squared minus 4x, where y represents the position of the duck in meters and x is the time in seconds. So what we would have here, this graph kind of looks like this, and apparently this duck dives under water here and then flies up. I don't know if this function continues to describe its motion. I doubt it, because it's not really quadratic what I've drawn here. But in any case, when it's under the water, that's what it's done. So the positions here will be measured from the top of the water, and that means that these positions will be negatives. So how long was the duck underwater? Well, first of all, I have to identify what I'm looking for here. This is how long. That's looking for a time value. In this case, x is time. So x equals how much? And we know that the duck is not underwater when y is bigger than 0. So if we can solve for y equals 0 here, then we can figure out how long the duck was underwater. So I plug in 0. I notice the c value in this equation is a 0 as well. That means that I have a common factor in these two terms. So I factor out the 2x. You could use the quadratic root formula here, okay? But I'm going to factor as many times as I can just to get you practice. And I get two answers here. I get x equals 0 or x equals 2, which is what my graph kind of shows. Here's when x equals 0. The duck started on the water, and when it went under the water, we started timing, and 2 seconds later it came up. And so the duck was under the water for 2 seconds. When was the duck at a depth of 5 meters? So that's going to mean a position of -5. And when says here's find the x. Remember, math's about me giving you one thing and asking you for the other. So I've given you the position, the y value. I'm asking for x. Whoops. So if we do this, plug in y equals 5, make one side equal to 0. We plug in, we get this negative under the square root. If you type that in your calculator, it's going to give you an error. A lot of students will just try and ignore this negative sign. But this negative sign means everything. It means that there's no answer to this. There's no real time when this duck was at a depth of 5 meters. And that's the answer. We conclude that the duck is never 5 meters below the water. So we can verify this. We're finished this question, but we can verify this by looking at the minimum value for y, the vertex. We don't have to do this, but what I did here was I solved for the x value. I see that when x equals 1, this is when it's at the minimum value. I plug it in, and I see the minimum value is -2. Well, if this is -2, of course the duck doesn't reach down here, ever. And that's why we had the negative under the square root. So don't ignore those negatives. They are important. They mean that that there is no answer to this question, which is an answer to the question. Not to get too philosophical. Anyways, let's take a look at another one. How long was the duck at least 0.5 meters below the water surface? So how long, again, is a time. I'm going to plug in y equals -0.5. This will tell me when the duck is 0.5 meters below. Okay, oops. So, make one side equal to 0. Here's the quadratic root formula. Please don't think that that's helping you. Me just kind of throwing this on the page. What you need to do here is you need to take this function. You identify the A, B, and C. Go back a few moments here and pause the video, and you write this out. You have to have practice writing this out. You have to have practice handling the root of 12. You have to have practice realizing that you have to do the numerator first, the adding and subtracting, then divide by 4. You have to make sure that you can get these answers. Okay, and if you can't get these answers, definitely post the question up to the discussion board, or I don't know, even take like a video of what you're typing in to your calculator so I can show you what's happening there. But we ultimately have to have this. And again, you can do this kind of in stages, right? You can say 4 plus the 3.46, then you hit equals, so that would be 7.46, and then you can divide that by 4. Okay, and that'll get you to 1.87 here, and you can subtract it, the 3.46, and get the other answer. So what we have here is that we know when the duck was at this position, but we want to know for how long was it at least below this. And so sometimes it makes more sense to talk about, you know, what if these numbers were a little bit easier? What if they were like a 3 and a 9? Well, how long was the duck under the water, or under 0.5 meters or below? Well, it was at 0.5 here, and then came back up here. So again, what this looks like would be kind of this. And so again, I made these numbers up, but let's say here's the 0.5 meters. There's the 3, and there's the 9. Oh yeah, so it's 6 seconds. So where does that 6 seconds come from? Well, that's subtracting those. So even though our numbers aren't as nice, the roots of our equations were 0.46 and 1.87, we're still going to be able to subtract those and find out that time interval. Okay, so that's an example of an easy question, quote unquote. I don't think any of these are really easy, but it's easier because you have this equation given to you. So here's an example where we don't have the equation, we just have information. Again, not much of a real life scenario here because your real life stuff actually, you know, requires people to know stuff about specific things like maybe physics or engineering or, you know, medicine or business or something. So we're just going to use a straightforward, quote unquote, real life example. So we've got this perfectly rectangular lawn. Somebody has perfectly measured out a strip of uniform width. For some reason, we know that this is 40% of the lawn remains unmowed. What's the width of the strip? So clearly, this is not real life, because if you want to know the width of the strip, you take a measuring tape and you measure it. You know. But in any case, again, it's just here to help you with the math, and it's simple enough that you, in terms of the scenario, so that you don't get bogged down with what the scenario means. Okay, so let's tackle this. First of all, what I want you to recognize is uniform means the same all the way around. So this distance is x, and so is this, and so is this, and so is this. And what that means is this unmowed part has dimensions. Let's see if I can get a color here that shows up. This right here, well, that is going to be 6 minus 2x, because here's 6. Then we're going to take away an x, we're going to take away another x, and this is what's left over, right in here. And then this is 8 minus 2x, because again, change colors here. This was 8, and we came in an x on this side and in an x on this side. So that's where we're getting So that's how we get the dimensions of that new rectangle. So the area of the old rectangle, the large rectangle, is 48, and 40% of that is 19.2. And so we can set up this new area here. 19.2 is equal to 8 minus 2x times 6 minus 2x. So I need to solve for x here. X is the width of the strip. My answer is going to be x equals something. So I have to solve this equation for x. And there are 2 of them here. So I'm not going to think about undoing what's being done. I'm going to think about foiling out that left-hand side, expanding the binomial, and then making one side equal to 0, then use the quadratic root formula. And again, this is here for you to try this, make sure that your answers match mine, and then we'll use the quadratic root formula. Then we get 2 answers. There are 2 answers to this equation, but there's only one answer to this problem. And so if I look at this 11.45, that fits in here, that works. But it doesn't work when I start subtracting 2 of those from 6. That gives me negative lengths. So there's no way that that's a possibility. this is the only answer. So the width of the strip is 1.25 meters. We can double check. If we take 2 of those away from 8, we get 5.5, and 2 of those away from 6, we get 3.5. Multiply that together, that gives us the 40% that we're looking for. Here's a different type of question. Again, not much of a real-life problem, but one that just will help you practice the math. So 2 numbers have a difference of 18. The sum of their squares is 194. What are the numbers? So what happens here is that I have 2 numbers, so let's make them variables. Please don't use X or Y or A, B, or C. I think you'll just get yourself confused. So I use my initials. If you need to borrow my initials, you may. So S is one of the numbers and G is the other. So that means that S minus G is 18. And the other, as you'll see here, the question, we're just translating. So the question gives us 2 equations. There's one of them. It says the sum of their squares is 194. So sum means adding. What am I going to add? I'm going to add their squares. So S squared plus G squared equals 194. And so now I'm going to take the simpler equation. I'm going to solve it probably for S here, since it's just adding G to both sides. And then I'm going to plug it into the second equation. Okay. Now I have a quadratic. I'm going to FOIL this out. Make one side equal to 0. Again, this is good practice for you to do at home. Pausing the video, making sure you can get these numbers. Make one side equal to 0. Use the quadratic root formula. Now I get 2 answers. These are not the 2 numbers that I was looking for. The question says, what are the 2 numbers? Well, the 2 numbers I have are going to be S and G. This is just 2 possibilities for G. So if G is negative 5, then S equals 13. Or if G is negative 13, then S equals 5. So the 2 numbers are either negative 5 and 13 or negative 13 and 5. So here's another example. Talking about area. Area of a rectangle is really great. Most of the time, it gives you this quadratic that you can deal with. Here I'm increasing each dimension by a distance of x. And so I want to solve for x here. So the new area is 80 because we've had 48 originally. Oops. We had this in here was 48. And then it increased by 32. So now we have 80. And that means that what we have here is this was 6, let's say. And so we added x to that, so that would be 6 plus x. This was 8. And we added x to that. And so there's our equation. I'm going to FOIL, make one side equal to 0, use the quadratic root formula. And so I get either x equals 2 or x equals negative 16. And of course, I can't have a negative length, but that can show me that answer though, and then cross it out. Whoops, I forgot about that. We already used that. And so the answer here is x equals x equals 2. And so we can check this. Right? 6 plus 2 is 8. 8 plus 2 is 10. The new dimensions will be 8 by 10. That gives me a new area of 80. And then there's one last word problem, kind of a classic one. They give you the equation here, but they ask you a bunch of different things. Okay, so here we have this ball being thrown, and it follows a parabola. This is actually physically true here. The physics of this is pretty accurate. This A value is more or less negative 9.81 divided by 2. Negative 9.81 is the acceleration due to gravity, but in any case, this is something that happens here. You throw something in the air, in the absence of air, it follows a perfect parabola. So let's ask a few questions about this. When was the height 3.5 meters? So when means I'm solving for t. this is going to be the height. Oops. Okay, so we have anywhere I saw an H, I'm going to plug in 3.5. I'm going to set one side equal to 0. Again, I'm going to use the quadratic root formula. The reason why I'm not finding the vertex is it didn't say anything yet about maximum or minimum or biggest or bestest. It just asked me when, and so I'm trying to solve for t, and that means I need t equals. And so when I get down here, I see that I get these two answers. These answers both make sense, right? I have this ball being thrown like this. When does it reach a height of 3.5 meters? On the way up, and on the way down, it could be at a height of 3.5 meters. Okay, so the shortest one is on the way up, and the other one is on the way down. How high is the ball after 4 seconds? How high asks what's the height. So I'm going to have h equals, this is the time, and so now I can plug that in. So after 4 seconds, the ball is 1 meter in the air. What is the ball's maximum height? Well, it's asking for height, so I must need to know the time. And of course I do know the time because of the word maximum. It screams vertex. So t equals minus b over 2a. There's the equation. T equals minus b over 2a. Plug it in. I just identify my a and my b value, and I use those. And so what I see here is that after 2 seconds, the ball is going to reach its maximum height. I can figure out what that is by plugging it in, and I see that my maximum height here is 21 meters. And when does the ball hit the ground? Again, when means t. I must have given you the height. It's hitting the ground when the height is 0. Okay, which is what I've said right here. So now I can solve. I get 2 answers here, one of them being negative, and so that can't be my answer. The ball hits the ground 4.049 seconds after we threw it. And the last question is, from what height was the ball thrown? Here I'm asking for height. The time here is implicit. We throw this and we start the timer. So the time here when we first start is 0. And so this is just asking for the y-intercept, which is 1 meter. So I would very much encourage you to look through the workbook. Understand that there's going to be some word problems there and there. And these are hard, right? Especially the ones without the equation. You have to really practice those. The nice thing about it is because they're so hard, I'm pretty much only going to evaluate you on the ones that I've gone over. There are lots of others, but I'm basically going to be talking about an area or a uniform width. We're adding something to both dimensions. In terms of the ones with the equations, those are a lot simpler, and so because the equation's already given to you, I can ask you anything. Vertex, x-intercepts, y-intercepts. When is it going to be at this height? When is it going to be at that height? What's, et cetera, et cetera. So, anyways, have a look through the workbook, and hopefully this goes well for you next week on the midterm. Okay, take care. We'll see you next time.